All right, this is worksheet 9.5. In this worksheet, we're going to look at Graham's law specifically. The other video talked about Dalton's law already. So if we go down to part B, Graham's law of diffusion and effusion is all about the movement of gases and their relative speeds. Okay, so we're talking about relative speeds here and how they relate to each other. So if we have two specific types of gases and we can say, hey, this gas is going to be faster and this gas is going to be moving slower, and we can compare those as long as those two different gases are at the same temperature. We're going to talk about two types of gases. Those are known as diffusion and effusion. And really what that is just the movement from an area of, here's your kind of key points here, high concentration to low concentration. And so you guys have all experienced this before. If you've ever been in a middle school or a high school locker room, and you have this is overhead view, maybe somebody's standing over here, and you're way over here, and let's say this person, well, that's you. This person sprays a bunch of Axe body spray or perfume or something, and that's a gas. And that's a very, very high concentration. There's very little, if any, Axe body spray over here. And so those start to move around the locker room. That's what the kinetic molecular theory says, is they just move in random orientations, but eventually some gas might migrate and it might come over here and hit you in the nose, and then you smell that gas. And so that's the kinetic molecular theory about, gases. They move in random directions in all directions, and they just kind of bounce off of everything here, there, and everywhere. And eventually they might, go from where we had lots of gas, which is over here, and they'll migrate to where we have very little gas. Okay. And so that's the deal there, right? That's diffusion. Effusion is really pretty much the same exact thing, except let's pretend this is a container that we've got here, and there's a small hole in that container. So I've got another box here, and let's say there's a small little hole here in the box. And effusion is there's a bunch of gas in here, and that's all moving around, bouncing off stuff, and it's just going to come through that small hole. So effusion is about an area of high concentration to low concentration inside of a container, which is, maybe you have a propane tank and it has a very, very small leak in it, and so then it's leaking out, and that would be called effusion. Both of them are going to have the same math involved with them, and both of them are going to be kind of treated the same, just, two different words there. I really wouldn't worry too much about the words. Just diffusion is high concentration to low concentration. Effusion is high concentration to low concentration in a container with a small hole. So then let's kind of get into the meat and potatoes here of like what Dalton's law of diffusion and effusion actually says. First, we're going to look at this from like a qualitative understanding. And there's a little bit of math here, so kind of hold on here. If we have two gases at the same temperature, earlier this year, we talked about how temperature is a measurement of movement, okay? And that is true. But when we're talking about two different gases, we don't use the word movement because this is true, right? If the temperature goes up, right, the speed of those molecules move faster. And likewise, if temperature goes down, the speed goes slower. But if we want to actually talk about what temperature actually is kinetic energy, which is the energy of movement. So if we have two gases, let's say gas A and gas B at the same temperature, well, then gas A and gas B has the same kinetic energy. So that's the first thing, right? If I have two gases at the same temperature, oxygen gas, helium gas, they have the same kinetic energy. And then you maybe remember from middle school, or maybe you've taken other science classes at high school, like physical science, you might have come across this equation. Kinetic energy is equal to 1/2 times the mass. M stands for mass. V stands for velocity, which is another word for speed. Okay, so 1/2 mv squared, mass times velocity squared. So we can say the gas A is 1/2 mv squared, gas B is 1/2 mv squared, and we can substitute that down here into equation number 4. We have the mass of A times the velocity of A squared, the mass of B times the velocity of B squared, and let's actually, get rid of A's and B's. Let's say A equals oxygen gas, and let's say B equals hydrogen gas. And so, it's not A and B, it's 1/2 the mass of O2 and velocity of O2 and the mass of H2 and the velocity of H2. Okay? And so then what you can notice is if I'm trying to simplify things, if you notice I have 1/2 on both sides, so I can get rid of the 1/2s and then I get this thing, right? And again, this would be O2, velocity of O2, mass of H2, and velocity of H2, okay? And maybe that makes a little bit more sense here. So we can say the mass of oxygen equal to the velocity of oxygen squared equals the mass of hydrogen times the velocity of hydrogen squared. And what you might notice here is these things are not equal, right? Oxygen has a mass of 32 atomic mass units, or 32 grams per mole. Hydrogen has a mass of 2.02 grams per mole, or 2.02 atomic mass units. So what we can see here is if these things are equal, but the masses are not equal, what we're saying here is if this mass is lighter and this mass is heavier, for those two things to be equal, that means this velocity must be going faster and this velocity must be going slower. So, what is the takeaway here? Here's kind of the big takeaway. The heavier gas must be going slower, and the lighter gas must be traveling faster. And that's kind of the first thing you just need to understand is at the same temperature, those two gases have the same kinetic energy. If they have the same kinetic energy, then the heavier gas must be going slower and the lighter gas must be going faster if they're equal to each other. And so that's kind of the first thing. Heavy gases go slower, lighter gases move faster. Now we can actually, rearrange this equation and get rid of the squares, and we're going to be left with this, right? And this is Graham's law of diffusion and effusion in a quantitative sense. And so we can say that, yes, hydrogen is going to be going faster, but we can actually calculate how much faster. And so let's go and plug these numbers in. So we can say the velocity of hydrogen over the velocity of oxygen is equal to the square root of oxygen's mass, right? This is the mass of oxygen, which is 32 atomic mass units, over 2.02 atomic mass units, or 2.02 grams per mole. And so what you got to do is you got to find the square root button on your calculator, and you got to type in 32 divided by 2.02, and the square root of 32 divided by 2.02 is 3.98. And so what we can say is hydrogen, H2, is 3.98 times faster. So we already know that the lighter gas is faster, but now we can say, hey, hydrogen moves around almost 4 times faster than oxygen at the same temperature. And so we can go down here. If you flip the page, we're going to have some qualitative things at first, and then we'll kind of get into some quantitative questions here, and I'll do a couple of these with you. It says question number 1, assume that gases in the following have the same temperature and pressure. Predict which gas in each pair would diffuse more rapidly. And so again, you got to get your periodic table out. And you got to look at CO2. If you look at 12.01 and 16 and 16, you can calculate that this is 44.01 grams per mole, or atomic mass units. If you happen to look at bromine, bromine's on the right side, it's 79.9 times 2. Bromine is almost 160, so this is 159.8 grams per mole, or atomic mass units. And so you can see that bromine is significantly heavier. So the question asks which one's going to be moving more rapidly. That would be CO2, right? CO2 is faster. And then the same things here. You got to figure out, nitrogen versus HCl. You got to figure out NO2 versus this one. And then CCl2, F2 versus SO2. And just kind of calculate the masses, just like we did in Unit 6 and Unit 7. You got to calculate molar masses. And then you can say, well, this one's 44 and this one's 160, and so the 44 one, must be going faster. When we go down to here, question number 2, If we have two gases, right, helium and oxygen, they're both at room temperature. First things first is which one has greater kinetic energy? Remember that kinetic energy is a measurement of temperature, so they are going to have the same kinetic energy if they're at the same temperature. However, if we get down to question number 2b, the velocity of helium to oxygen. Okay, so this is going to be the velocity of helium over the velocity of oxygen is equal to the square root. Remember, oxygen is 16 and 16, so it's 32. Helium is 4. And so then you can plug those numbers in your calculator. Square root of 32 divided by 4. And I got 2.83. 2.83. So what we can say is helium is 2.83 times faster. Okay. And so that's going to be, kind of what this worksheet's about. If you have questions, please, ask your friends or ask me, and we'd love to help. I know this is challenging, but I know you guys can do this. So give it a good show. And if you have questions, let me know. Thanks.